Okay, let's look at an open flow device, not a closed system, but an open device that produces work, and that is called the gas turbine. The gas turbine is modeled as a Brayton cycle. Brayton cycle is used to represent a gas turbine. So how does a gas turbine work? Well, it uses one compressor, or perhaps multiple compressors. We'll talk about that later. It uses a compressor to pressurize air. So air is inducted into a compressor. It is then compressed up to state 2. If this is the ideal Brayton cycle, the compression occurs reversibly and adiabatically. So let's draw the TS diagram here. So let's draw the TS diagram as we go along. We start off at state 1. And then if we're dealing with the ideal Brayton cycle, we have reversible compression up to state 2. In the compressor. And then the compressed air is then fed into a combustor, which is approximately an isobaric device where fuel is injected and then burns. So this is a heat addition process occurring inside the combustor. And so we're modeling this as an isobaric heat addition process. So we have heat addition going on, Q inside the combustor. I'm calling it Q combustor. It's really Q in. Okay, up to state 3. Heat addition up to state 3, and that's an isobaric process. And then, so that brings us to state 3, isobaric compression in the combustor. And then we have expansion in the turbine where the work is extracted. Energy is extracted from the flow, producing work. And so if this is an ideal Brayton cycle, we have reversible expansion in the turbine. So pressure and temperature fall, assuming it's an adiabatic turbine. Pressure and temperature fall, and we end up at state 4. So we exit the turbine. Now, how does this device actually produce power? Well, some of the power produced by the turbine. The turbine's producing power, and the compressor is consuming power, okay? Some of the power produced by the turbine is fed in to drive the compressor, and the remaining power left over produced by the turbine, the net power, W dot net, which is the difference between the turbine and compressor power, that is your net power output for the gas turbine. So it's critical to understand here. Some of the power produced by the turbine, W dot turbine, is fed into and drives the compressor, and the remaining, what's left over, W dot net, is the net output for the gas turbine, okay? The heat rejects, so the exhaust at state 4 is then rejected into the environment. The environment basically is at constant pressure, 1 atmosphere or something like that. So the heat rejection process is assumed to be isobaric. So we have Q out. We're not really interested in Q out too much. Q combustor or Q in is what we're really interested in. So let's go over the characteristics of the ideal Brayton cycle one more time. It uses a combination of open flow devices, compressor, combustor, and turbine. The turbine drives the compressor, and the net work is W turbine minus W compressor, or W dot. If this is an ideal Brayton cycle, the compressor and turbine operate reversibly as well as adiabatically. The heat addition process in the combustor is isobaric. So we're injecting fuel into a chamber. The fuel is burning, releasing heat, and it's assumed that that occurs isobarically or nearly so. And then we have isobaric heat rejection going on in the environment. So those are the characteristics of the Brayton cycle. Those are the characteristics of the Brayton cycle. So let me write these one more time over here. We'll write it over here. So again, for the ideal Brayton cycle, For the ideal Brayton cycle, compressor, turbine operate reversibly, constant pressure heat addition and rejection process. We have process 1 to 2, which is adiabatic, and therefore adiabatic reversible, and therefore isentropic compression. So it's reversible. Reversible adiabatic, therefore isentropic. And then from 2 to 3, we have isobaric heat addition in combustor. From 3 to 4, we have adiabatic expansion, and it's reversible in the turbine. So this is the compressor, and this is in the turbine. And then we have isobaric heat rejection going on in the environment. Isobaric heat rejection in environment. Okay, so we're modeling this as an isobaric heat rejection to the environment, okay? Into the environment. Now, this idea of having reversible compressors and turbines. So the idea is not only are these adiabatic here, but they're reversible and therefore isentropic. Not really very realistic. Let's try to inject a little bit of realism here into our Brayton cycle. Make it more realistic. So there's the non-ideal Brayton cycle, which allows for inefficiencies, irreversibilities in the turbine and compressor, and maybe if you want to get really adventuresome, a pressure drop in the combustor. Pressure drop occurs due to the acceleration of the flow as it gets heated up. As you heat something up, the density goes down and the flow velocity has to increase to maintain m dot. There's also maybe some friction going on in here. So we may have a pressure drop in the combustor. We certainly have possibly inefficiency in the turbine and compressor. So for the non-ideal Brayton cycle, we have efficiency for the turbine and the compressor. So eta turb and eta compressor, these are isentropic efficiencies. These might be not equal to 1, or I guess I'll just say they could be less than 1. So in other words, irreversible. We might have irreversible turbine and compressor operation. We also may have pressure drops across the combustor. Could be a delta P across the combustor, COMB, delta P across the combustor. Let's see here, the combustion occurs, the combustion in the combustor occurs from state 2 to state 3, the heat addition in the combustor. So there might be a delta P, which is P3 minus P2. So that may not be, that may be less than 0. So there might be a pressure drop across the combustor. Might be a pressure drop across the combustor. So these are all possibilities. How does this change our TS diagram? How does this change our TS diagram? For a more realistic gas turbine involving the possibility of pressure drop in the combustor and inefficiencies in the turbine and compressor. So again, we'll start off at state one. So here's state one right here. Now, let me put in the isobars. Let me put in the relevant isobars here. In fact, I think, let me go back here and make sure the isobars are included. Let's put, so this is our P max, maximum pressure isobar. Here's our P min isobar. Let me put some of these isobars into our TS diagram. So we have our P min, we have our P max. There's our P max isobar right there. Let's see here. The reversible compression from state one to state two would look something like this. So here's 2 sub S. This is the isentropic compression process, but we don't have an isentropic compression process. We have a process involving some delta S. So here's state two right here. There's 2 sub S, that's the isentropic. That helps us define our isentropic efficiency. We've done this stuff before in the chapter on entropy when we talked about turbines and compressors. Then we have maybe a pressure drop. So here's P max is equal to P2, and here I have P3. There's our P3 isobar. So we have a pressure drop. We start off at a high pressure P max, and then we drop to a lower pressure in the combustor. And so this is state 3 here. There's state 3. Delta P across the combustor, delta P. And then we have the isentropic expansion process. So this is to 4 sub S. But the real turbine has some inefficiencies. So state 4 is actually a little bit to the right, okay? So we have the heat addition process going on here in the combustor, Q combustor, and then we have the heat rejection process going on there. So the ideal process would have vertical lines for the compression and expansion process in the compressor and turbine. The real processes have a delta S because they're irreversible. And then we maybe have a pressure drop in the compressor, in the combustor. In the combustor, maybe. So that's what the TS diagram looks like for a non-ideal Brayton cycle. If you want to know what the expression for efficiency of a Brayton cycle is, note the expression for the efficiency of a Brayton cycle, assuming constant specific heats, 1 minus 1 over R sub, let's see here, let me make sure I'm using the right notation here. Remember, R is a compression ratio in our, in our closed systems, Otto cycle, diesel cycle, whereas, R sub P. R sub P, K minus 1. Now, what's R sub P here? R sub P is the pressure ratio. So it's P max over P min. Pressure ratio. So the efficiency for the Brayton cycle, 1 minus 1 over RP, pressure ratio, K minus 1 in the exponent. What this means is as the pressure ratio goes up and the maximum pressure gets higher and higher, we squeeze the air down as it goes through the compressor more and more, do more compressor work. As the pressure ratio goes up, this term goes to 0 and efficiency approaches 1. So the idea here is, as the pressure ratio goes up, so note, as the pressure ratio goes up, the efficiency of the Brayton cycle also goes up. Currently, pressure ratios, depending on the engines, are about 30 or so. So in the gas turbine that you see on the airplane that you ride, so the airplane usually utilizes a Brayton cycle, the gas turbine, it's going to be on the order of 30 or more. So pressure ratios have been going up and up and up to increase efficiency, okay? Now, I'm not going to go through the derivation of this expression. What I invite you to do is note that this actually looks a lot like the Otto cycle, except it's constant pressure heat addition and rejection instead of constant volume heat addition and rejection. Go through and look at the derivation for the efficiency of the Otto cycle and see what changes if we have constant pressure heat addition and rejection instead of constant volume. The answer is almost nothing changes. The only difference is you'll have a CP instead of a CV at some point when you calculate the heat addition. The CPs and the CVs cancel out and you get exactly the same expression, the exact same development for deriving the efficiency of the Brayton cycle as for the Otto cycle. So I'm not going to go through the derivation of the Brayton cycle efficiency. I do want to hold you accountable for it, so why don't we put a box around it? Because the derivation is exactly the same as for the Otto cycle. No difference, and the equation is the same, except this is a pressure ratio instead of a volume ratio. Okay, so I'm not going to go through that derivation. All right, let's take a break for a moment. Let's do an example involving a non-ideal Brayton cycle. Let's do an analysis here.